Hello, everyone. Welcome to the last conference on our data track for today. Today we have with us Ollie Green, data scientist at Amazon London, using time series analysis, classification, and deep learning to optimize demand planning in his daily work. And he will be presenting for us Make It Simple, Machine Learning in Time Series Forecasting Development to Deployment with Python. The stage is yours, Ollie.
Thank you so much, Amira. Hi, everyone. I am Ollie Green. I'll make a quick adjustment and say I'm not a data scientist at Amazon. I am a business analyst, but we'll get into that in just a second. So today's topic, we're going to make it simple when it comes to machine learning in time series forecasting, going from development to deployment with Python. This is going to be our agenda. I'm going to talk a little bit about who I am, why I'm interested in this topic, and why we should talk more about this. We're then going to dive into the problem in time series analysis and why we would like to make it as simple as possible in at least many of cases. Then we're going to go into some Jupyter notebooks and look at our setup for these kind of analyses, talk about some models, a little bit of evaluation metrics, and then in the end, deployment considerations. And by the end of this should take 25 minutes. We have 5 minutes left for questions as well. Let's dive into some introductions. My background, I'm currently a business analyst at Amazon in London. I wrote my master thesis there earlier this spring in terms of machine learning and deep learning specifically, and LSTM modeling for time series analysis, specifically within logistic and supply chain. I was an intern there earlier this spring and landed a full-time offer earlier this autumn. I founded last year a company called DataAlliance.io, which basically is a Swedish company that helps Swedish organizations to get further into using machine learning for business insights. I was a speaker at PyCon Sweden last year talking about the world's most powerful NLP model, which is GPT-3, which also was the algorithm that helped me become a machine learning author, where I used this algorithm to basically write and publish a book on Kindle, a small little kid's book about a robot named Bob, which everyone can check out on Kindle if they want to have some bedtime stories for their kid that is written by AI. And finally, I did my master's in operations management at Stockholm University. Some context also for what I'm working with, specifically within time series forecasting, is I'm currently working at Amazon Shipping in UK, where similar services as PostNord, Royal Mail, DPD, etc. And some examples of projects that I'm very passionate to working with at Amazon is time series forecasting. So we're trying to predict future demand with limited numbers of data. Customer segmentation. So how do we classify different customers to, in the end, understand how they are supposed to be purchasing stuff in the order. And finally, new market launches. So you can take time series analysis, but then with limited data. How are you going to approach these types of problems is something that I feel is very interesting to work with. But note, this presentation has nothing to do with Amazon, and all data that is generated here is for just illustrative purposes. Okay, let's talk about the problem in time series analysis. The one thing that we can all agree on is that 100% certainty, we can say that we cannot predict the future. Basically, what we're trying to do here using statistics, mathematical modeling, is to find some way that we can get as close as possible to what we think the future demand is going to be for a product, service, etc. But then, of course, we want to understand what can we do? What certain factors can we take into consideration? How can we actually predict the future? One of these ways is to use some statistical methods of analyzing 3 different parameters. These are usually classified as long-term movement or trends. You can say, for example, if a company has 3% annual growth per year for the last 10 years, maybe you can assume that it's going to be approximately 3% growth for the next year as well. So see if you can see some common trends over long term. Short-term movements, that is broken down usually into seasonal variation. So for example, you can have holiday seasonality. So maybe it's more demand during Christmas time, and cyclical variations is different. Random and irregular movements, we come into something that we basically have just something that we have much more difficulty to kind of predict. And for illustrative purposes, let's take a look at this graph instead. At the top, we have an observed time frame with demand. We find that we can break a few components out of this. First of all, the trend that we talked about is a positive trend over time. We see some sort of seasonality, in this case, weekly seasonality that goes up very clearly on certain days and down during certain days. And then in the end, we have random fluctuations that is in theory more difficult to kind of predict. But these are the things that we're trying to figure out. The trend, the seasonality, and by removing those and trying to figure out how we can predict the randomness and then adding on top of that the seasonality and trend is kind of where we're getting with classical statistical methods and modeling. Now, for today's talk, we are going to talk about PyCon's newly opened fruit shop. This fruit shop is only selling oranges, and PyCon Sweden, they have talked to us and said, we want to figure out how much oranges are we going to sell and how should we predict this demand for oranges over time. The problem though is for our customer info is that they just sell to people. We don't have anything other than at the end of the day, the people who sell these collect the demand of how many oranges we sell. So the data we have is something called univariate data, where we just have one column of date and one column of just the demand per day. Something worth noting here is that in a very big time aspect, usually data cleaning and pre-processing is a big part of time series forecasting. For example, if you're missing a value, or you're supposed to take the missing value as the mean between the two previous values, there's multiple methods and ways of doing this, of basically filling in empty values, for example. What we have in this scenario is just clean data. So we're having a little bit of lucky coincidental data here then, so we can just dive into the more interesting areas, which is the modeling and the deployment parts of time series forecasting. So now let's jump into the Jupyter Notebook. Perfect. So we start off with the basics. We're importing some modules. In this case, we have the basics of pandas, numpy, matplotlib for some visualizations, and pytorch for a little bit of more deep learning, machine learning, algorithmic computations. Nothing exciting to see here, so let's go into the data part. We start off by taking our data and reading it in. We get a little data frame where we can see the sales. And in the second row here, you can find that we add the weekday by using the datetime function and just getting the day of the week. This is to illustrate that we might want to see if there's any sort of like weekly seasonality for oranges in this case. Now, we want to get a general gist of how our data looks. So we do a quick visualization here and see that we have a very, very odd looking time series graph here. But to decompose it a bit, it seems to be something that has some sort of maybe like monthly or weekly seasonality, but the looks of it, it goes up and down, up and down. It's not very clear line all the time. And then we see very big jump in the December month of 2020. And then we see a bit of a jump in the December phase of 2019 as well. It's much smaller here on the picture, but it seems to be a little bit of a bump here. So let's start by seeing if we can find some sort of seasonality here that we can use for our time series analysis. We start by just grouping basically the weekdays and the sum to see, are there some days that are more on average sold oranges than others? And we can see here that we have much more oranges being sold in the beginning of the week than later. In this case, weekday 0 is a Monday, and then it goes number 1 to Tuesday and so forth. So we see that the lowest number of oranges sold are on Saturdays and Sundays. Summary: high demand in early weekdays, lower demand in the end of the weekdays. And it seems to be that this seems to be a consecutive trend. So we can see some sort of weekly seasonality that we want to use for our analysis. We then take up some evaluation metrics. And the one thing that I want to open up for kind of thought to discuss is basically accuracy metrics. Usually this is something that's standardized in larger organizations, so it depends if you have a smaller or a large organization for this. But you can have, for example, from sklearn here in the note section here, mean absolute error is a common one, mean squared errors, etc. We have then also, this case, a accuracy metric called WAPE. In this case, it's called weighted average percentage error. This is basically just taking sum of the absolute deviations between the forecast and the actual demand, and we divide it by the sum of all of our sold oranges. So we write a little function here, and we get a WAPE. And the one key thing here for us, an accuracy metric for this one, the lower the number of WAPE, the better. So we want as close to 0 as possible. Then for testing and training purposes, we split our data. In this case, we use 10%, which is roughly 60 days for the testing data, and then we have the rest of the days for training. Now, we can start off by looking at some simple statistical models. Here we have weakly naive models to start with. Why do we think that this might be a good starting point? Well, coming back to the kind of analyst or the data scientist position is like, okay, where do we start to get a good foundational model to use as a benchmark? And we saw that it seemed to be a weekly seasonality. So maybe we can assume that a good starting point is to say that if we have a model that takes last week's demand to say that that's the next week's demand. So basically this Monday is supposed to have similar demand to the next Monday. That could be a good starting point to see what the weighted average percentage error is, or the WAPE. In this case, we run this and we get 30% roughly, or 31% in WAPE. We then take a moving average. Why a moving average? Once again, it's a similar model where we take the previous day's demands and we just take it and average them out to see if there's some recent fluctuations in the demand, and we apply that to the next day. In this case, we got a WAPE close to 17.4%. Basically, what we're taking away from this is not the complexities of the model, what they're doing, etc. What we need to understand here is using them as benchmarks. This tells us that if we use an more advanced model, it should not give us a higher WAPE than 17 to 30%. So that's the key thing to take away from this one. Moving on to our machine learning. In this case, we use an LSTM using PyTorch, and the key, arguments and assumptions that we make here is that we use a test data size. So basically how many days was the 10%? We use 60 days in this case. We split them up in train and testing data. We use a little bit of min-max scaling so we can transform them into smaller numbers. So it becomes easier for the deep learning model, in this case for the PyTorch model, to be able to basically get the computations more easily. And it's going to be quicker for us to get the epochs and the model to run, so to speak. Continue from this, we run through some baseline setting up of the LSTM class. We set up the model. We use 250 epochs. And since this takes a little bit of time, I ran through this model earlier today. And in the end of all of this, we get a WAPE of 32%. So the takeaway here is that we had a model, a deep learning model, and just for the principle's sake, we don't have to use always a deep learning model to get really accurate results. We could use something as simple as a naive model or a weighted average model, weekly average model, to get even better results than a deep learning model. So basically, more complex isn't always better. You can, of course, tune this, more epochs, or you can make different training windows, experiment, of course. But this is then the good starting point. If we just use this model compared to the old one, we should stick with a naive model or the moving average model since they're better, and there's some other factors we want to consider as well. However, next step before production, we want to basically do a little bit of a root cause analysis, because it's easy to do the time series analysis, just focus on that, and then we stop. It's very important in large organizations to utilize their findings in some proactive manner. So in this case, figure out why the weekend is so much lower in demand. Is that something that's going to stay the same, or is it something that we need to basically be aware of that might change? In this case, we go to the sales organization, and the people who sell our oranges at PyCon Sweden, they have found out that our customer says that oranges are weekday fruits and kiwis apparently are the weekend fruits everyone buys. But then it seems to be that during the holidays, everyone makes some special orange desserts. So it seems to be holiday speciality to make some special desserts, and then weekday being just a cultural preference for oranges. Interesting to know. In this case, we just take that and then we can apply maybe some sort of business strategy of selling kiwis, or understanding that our supply chain should be always ready for early, heavier demand during the beginning of the week, and then we can relax that and maybe adjust employment, like structures, etc., for that demand changing from the week. But now we come to an interesting point, which is, what did we miss in this methodology? So let's go back to our deck real quick. And here, I think that should be it. Yes. We did miss a couple of things. First of all, we took 10% of the end of this data set and just used that as testing data. And as you can see here, we're basically training the model on a very similar looking trend, and then we're testing it on a very different type of scenario. So here we introduce the concept of basically of validating our time series models, because a regular split might not be the optimal way of testing this. Instead, we can use something, a cross-validation method called sliding window or expanding window, which is very popular then in time series analysis. In the sliding window principle, we have more data where we can basically test maybe January to March and then test it on April. And then we can move that from February to April and test it on May. And then we move that forward. And so we can basically validate how our accuracy is for each month and moving that forward, instead of just having one specific month, which could be in effect targeted to seasonality and so forth. Expanding window is a popular model if you have less data available. If you have, for example, a new product that you want to sell. So the kiwi situation in our case, we might use the expanding window, and the sliding window might be something that we use for our orange, selling of the oranges. Now, this could be the illustration that shows this more vividly. So we could have it 50-50 in the beginning, and then we move it forward a bit when we have this not sliding window, but instead, once again, to the right, the expanding window, and moving that forward one after another to validate that we always get good accuracy. Okay. The other thing that we missed in our quick analysis, that we just said that we wanted just accuracy. However, there's something also very important when we talk about time series analysis, and that's bias metric. In this case, do we have something that is consistently missing the target, basically? So we have to the dartboard to the left here, we are hitting it all the time. We have no bias, we have full accuracy, like brilliantly made. We have very good accuracy in the right one. We hit the same point, but we're not hitting the mid target. So in this case, we want to be able to, in supply chain or in finance, etc., when we use our model, are we consistently under or over forecasting while we're having good accuracy? Becomes very important. Moving on from that, we want to run some experimentations, especially when we use statistical models such as the naive model and the moving average models, etc. We basically want to use something called Monte Carlo simulations. What we do is we basically repeat random sampling to get the likelihood that is for the range of an unknown quantity. Long story short, we basically try to simulate and see what is the best model to use for maybe a moving average weight. Should we look at only the previous Monday? Should we look at the 2 previous Mondays, etc.? So we can test how that actually works most optimally over a period of time. Then, of course, we want to test assumptions before production. So you can use, for example, a smaller sample size for specific customers. which is also going to help you if you come to larger organizations and try this, because getting approval from management is one of these things that is, to me, very easily forgotten when you just love to just work with the mathematical modeling part. But sometimes you actually need to get someone to approve this and actually explain it to them why this is a good model for this situation. Now, we have, I think, 5 minutes left, roughly, if I'm not incorrect, before questions. So let's talk about some deployment and model considerations. First of all, uncertainty. What are the things that we know we have not considered in this model? For example, when we had the moving average model, we are not anticipating an increase in sales. We're just taking the previous weekdays demand and just apply that to the next week. Once again, if we know that it's going to be increased demand during the holidays, we should probably incorporate that in our model. And also, of course, what is the most costly? As we talked about opportunity costs, we're talking about the over or under forecasting in this case. Is it more costly for us to, for example, let's say we sell our oranges at, I don't know, let's say 30 Swedish crowns at margin. So we maybe sell them for 40 crowns and we have cost of 10 crowns and it's 30 crowns profit. We want to understand, can we maybe buy a lot of apples to get up to this and not miss out on another sale? Would that maybe be more costly? So maybe we want to over forecast a little bit rather than under forecast because it's going to be more profitable in the long run. Benefit for Python using here is basically it's easy to work, as you know, for just editing the code and also like the modeling and assumptions. Jupyter Notebook, of course, is one of my favorite tools for this, as it's included with Markdown, so you can explain your reasoning and principles during your code. Scalability. How easy is it to change your model? And is it required some sort of critical speed? This is, of course, going to depend on industry. Finance is, of course, going to be very interested in high frequency and highly efficient algorithms, while you may be in a retail store, maybe just update it once a week or once a day. So speed, of course, Python might be suboptimal to C++, but if you want things to get done quickly and you need to make adjustments and so on, Python seems to be a more preferable language, at least in my experience. You have other solutions also that can handle these more efficient times. So Python and Numba, I haven't tried them out myself, but it seems to be the implementation of Python, but then applying this Python and Numba onto it, and it becomes similar speed to C++. Worth checking out if you need more speed, but love Python. Explainability. One of these things that are very easy to forget, at least it's been for me, is when you have, for example, an LSTM model or some sort of more complex machine learning model, sometimes you might not be able to explain what your model is doing and why it's doing it. And this could, of course, be very problematic if you have some sort of compliance and legal obligations to disclose from your company or to the government, etc., etc. So if you can choose a simpler model, as we talked about, a naive model that is performing better than your deep learning model, start with that and then train the model on the side while you have the more explainable model in production. Finally, the size of the data set. So for example, in machine learning, having a small data set, if you in the beginning of a new product launch, if we, for example, this case, going to start selling kiwis, having a machine learning model that we train on a few days of data, of course, is going to give us very odd results. So remember to make it as simple as possible. Start off with some easy statistical models, and what has been proven throughout many forecasting studies and competitions as well. I think it's called M3, if I'm not incorrect. ARIMA models, Holt-Winter models are usually a good starting point for you to just get good accuracy and before you go into the more complex algorithms. Formatting, when it comes to being, once again, as simple as possible, is just better usability. Once again, take the stance of understanding when you would be using this forecast, how would you want it to be delivered as well? So something that is very easy, of course, is to get it to a CSV file and maybe email it to the stakeholders or the users of this forecast. It's easy to forget this step, but once again, talk with your people who are using your forecast and find the optimal way of doing this. Of course, if you find something that is way more efficient, pose the question if you could change it to what they prefer, but remember the end user. Bonus, since we have maybe 1 minute left, it's also worth considering if you have something that is seasonally based. You don't have to have one model for forever. You might have it, for example, during holiday season and one for the off season. So in this case, we might do one model that works from January to maybe like September, and then we could do something for October to December. Worth having into consideration, you don't have to force one algorithm into all of this, especially if you do statistical modelings and not the machine learning and deep learning models. So to summarize, spend time on structuring your analysis and validation so that you can always find that your findings are correct and usable, because it's going to cause you less problem and be much more lovely in the end of the day. Start simple, set up good benchmarks and validation methods and accuracy metrics, bias metrics, and so forth, and work your way up from there. Here are some other resources if you want to continue learning a little bit about time series forecasting. Machine Learning Mastery is a website that I've used frequently to get on hold with some new models. AWS have courses for enterprise machine learning, and I'm also available on YouTube if anyone enjoys that. I wrote and published a book and wrote about my journey for doing that. That is all. Thank you for listening, and I'll open up for questions. Cheers.
Really great presentation. So we have 2 questions, actually. The first one, can we try ensemble technique over this?
Brilliant question, Roik. I hope that I pronounced that correctly. Ensemble methods has been very prominent in Kaggle competitions and general forecasting. So absolutely, ensemble methods are something that's been frequently used in recent years. And that will be, of course, other steps that you can move on to. And for the audience who haven't heard about ensemble technique, is you can basically take multiple models, group them together, and then you can take maybe the average value of those models, basically finding a middle ground between multiple good models, and then hopefully find the best optimal one in all of these models that you use. So for example, you could use the naive model, you can use the moving average model together, and then maybe take the mean value or median value, average value of these two models, for example, and that might be giving much better results than just picking one of them. So definitely, ensemble techniques is a very good note to this as well.
Great answer to that. And we have another question. Hello, Oli. Any particular reason why you chose an LSTM model for this exercise over other ML algorithms for time series forecasting, like CNN or MLP?
Hi, Alan. Great question. There's multitude of different types of deep learning algorithms. I've just had some experience with LSTM recently, so my straight answer for this is that's the one that I have the most experience with, and therefore I picked it for this talk to get some sort of benchmark for a deep learning model. But you can definitely find multiple different ones, and they come in every year in some sort of new study for improved modeling techniques as well. So I would only suggest to be someone that's not like me for this year, who just pick one and dive deeply into that, but dare to check out multiple different variations of deep learning techniques as well. Thank you, Alan, for the question.
Oh, it was really a pleasure to have you with us, Oli, today. And I think this is a great way to wrap up our first day on the data track at PyCon 2021. Thank you for your presence, and talk to you soon, I guess.
Thank you. Talk to you soon. Have a great day,
Bye.
everyone. Cheers.
Bye.